Hello everyone and welcome to my presentation on No Cloud on the Horizon, Probabilistic Gap Filling in Satellite Image Series, a joint work that we are presenting at DSAA 2020. So let us dive right into it. First of all, we need to talk about satellite image series, or actually remote sensing in general. What is it all about? Well, remote sensing is about the acquisition of information about an object without making any physical contact with it, and therefore it's predominantly used for geography, land surveying, and also earth science in general. What are we talking about data-wise? We are usually talking about spatio-temporal data that is coming from satellite or aircraft-based sensors. And as you can guess, there's been an increased automation of the whole data processing chain, also with the help of machine learning and artificial intelligence. So the main issue that we want to talk about today here is the possibility of having gaps in the data. And that obviously hugely diminishes the usability and the information content of any data set. So how do these gaps look like? Well, let's look at some examples. On the top row you see some images with black stripes and lines on it. And on the lower row you can see the problem of cloud cover, where clouds are covering part of the surface that we are really interested in. So as you can see, there are very different reasons for having gaps in the data. You might have sensor failure, you might make mistakes in calibration, or you just face the problem of optical occlusion. And also this is not a specific problem of remote sensing only, but it's happening in all kinds of data domains. And all that leads to erroneous or missing values in the data set. But the good thing is, machine learning can help us to fill gaps and predict better values. So let us look at our methodology at a glance. So on the left-hand side you see the cloud-covered pictures and you see that it's incomplete. Also, there's a very important point. This is the only data we assume to be available. So we don't assume that there's fully observed training data available or pre-trained models on cloud-free or gap-free data. This is the only thing we get. And on the right-hand side you see the predictions made by our method. You can also see the spatio-temporal dimension, so you have several pictures of the same region over time. That gives you a spatio-temporal dimension. And what we perform is probabilistic gap filling, and for that we are using spatio-temporal Markov random field models. So one important aspect that I want to cover straight away is that we actually decided to go for a local model that is shifted over the whole dataset. You can see that on the lower part. So you only take one pixel over time together with its spatial neighborhood information, and you use that for training a model and also to predict the values in the gaps. And when you shift the whole model over the dataset, then you can fill all the gaps in the dataset and get a cloud-free, gap-free image in the end. Alright, so let us look at our methodology in more detail. As I said, we want to perform probabilistic gap filling, and for that we are using probabilistic graphical models. Or more specifically, Markov random fields. Those models always describe a random variable over some discrete state space. And the important thing about graphical models is that statistical relations between the different components of the random variable are actually represented by a graphical independence structure. So that graphical independence structure is very crucial because it allows us to perform the probability mass of being in a specific state. And we do that over the clicks of the graph. So we compute the probability of one click being in a specific state, and by marginalizing over all clicks we can put it all together to assess the probability of the complete model being in any specific discrete states. And we also need to train that model. As I said, it's not pre-trained or something. So how can we train such a model? For that we use maximum likelihood estimation of the parameters. So we have a data set with n samples. We take the probability mass of the clicks and the whole model being in those states, and by summing it up all over the data set we can estimate all the parameters. And one important point that I already want to mention here is the small regularization term at the end here, because that actually puts some assumptions on the parameters theta, and it's all weighted by a lambda value. So we will come back to that later. This is already a pretty solid framework, but there are still some open questions, and the most important one is how can we train a Markov random field with incomplete data? So let's look at that. As I said, we want to enroll maximum likelihood estimation, but maximum likelihood estimation demands gap-free data. So what we do to counter that is we first enroll the whole training in an EM fashion. So we first run an expectation step that is using Gibbs sampling to sample some values from our distribution and fill the gaps with them. Then we have a complete data set and we can run maximization. So we run a regular maximum likelihood estimation based on the Gibbs samples. And if we alternate both steps, this actually converges to a proper training routine, and we are able to train with missing data. Because the Gibbs sampling is always depending on the lastly trained parameters and vice versa, so it's always changing a little bit in that alternating fashion. But that is actually not enough. So as I said, we don't make any assumptions, so we might have one image at one specific time being completely missing. So how can we handle that? I mean, Gibbs sampling will lead to totally random values for all nodes describing that acquisition date, because there's no data available. And then the maximization will fit random parameters to those random states, and that's not going to work out. So what we do to counter that is we want to incorporate some kind of empirical prior information during the training routine. And obviously we do that with the regularization term. As I said, regularization always puts some assumptions over the parameters. For example, the popular L2 regularization enforces parameters to take values near zero. And what we came up with, that we just use a prior vector sigma that has some values in there that we want to enforce on the parameters. And the good thing is, the model can always differ from that, because it's all weighted with lambda, and we can control how much the regularization impacts the training. So how do we get those prior values now? There could be one approach by just asking an expert, but we said we don't want to have any ancillary information, so this is out. What we do instead is we empirically estimate prior values from the data itself, from the incomplete data. And we came up with two approaches. So one thing, as I said, the whole model is only handling discrete states, but each discrete state also has a multi-dimensional intensity or color value behind it because of the sensors. And what we can do is, by looking at the discrete states, we can compare the similarity of both states and weight the parameters accordingly. So we say very similar colors will have a high probability of transitioning from one state to the other, while very dissimilar states won't have such a high probability. And we call that the Euclidean similarity prior, because it's all based on the Euclidean similarity of the states. The other thing that we came up with is a transition probability prior. And what we do for that is we look at the incomplete data, and there will always be some transitions observed, maybe not many, but some. And that way we can estimate the empirical probability of a state transition and use that as a prior vector. So how does that whole prior training now come into effect? Let's look at the basic example. So this is the synthetic data set. We have 4 images with 64 by 64 pixels in that chessboard look. And at t equals 2, the whole image is missing. And when we don't use any regularization, you can see the result on the left-hand corner. It will be totally random, and it looks terrible, right? It doesn't look like a proper gap filling looking from t1 to t4. That looks very out of place. When we use the Euclidean similarity prior, we actually predict something that is very similar to the data observed at t1 and t3. So red will stay red, for example, because it's the most similar state. And obviously with different data it won't look that clean. It might be a little bit different, but similarity might be a good indicator to look for when estimating the parameters. So the other option was the transition probability prior. And actually what is happening here is there are some transitions observed over time from T3 to T4. And that actually allows us to predict something at T2. So for example, we observe that red changes to blue. And that is also what's happening here. And we can also see that black is changing to white from T3 to T4. And the same thing will be happening from T1 to T2. As I said, the whole prior thing is all weighted, so you can always adapt that to your needs. It's a very neat way to incorporate that and deal with missing data. Right. So let's look at another problem. Another problem is that we actually want to fill gaps. Now we have the whole model trained, that's really good, but how can we fill the gaps? What we do for that is that we compute the probabilities of being in a specific state given the observations in the model. So we're looking at each subslice in the data, look at what is observed, and estimate the stuff that is, or the values that are missing. Right. So one approach to do that is to use the maximum a posteriori state, so the most probable state given our observations. And the other approach that we came up with is to actually compute the probability of all possible states and merge them all together into a superposition state. And we evaluated both approaches, both are valid and give some good results. So it's really up to adaptation to choose one of them. So that was a lot of theory. Now let us look at some experiments and real data. First of all, this is the region where our data is coming from. You might not recognize it, but it's actually the area where I'm living in and also the area where a lot of the authors are placed in. And it's a region from Germany, Dortmund, during 2018. We also ran experiments on a different region in France. We're not discussing that in the presentation now, but it's all in the paper, so feel free to have a look at that. So let us look at the proportion of clouds during 2018. As you can see, we have 20 different acquisition dates, and all the gray bars here show data where there's only clouds available. So there's no captured data over the surface of 1000 by 1000 pixels in the image. And what you can also see here is that on the dates where there's a lot of observed data, so big green bars, we also added some artificial clouds. And that allows us to evaluate how good our method works and also compare gap filling results. It's a really neat idea to compare it and evaluate our whole approach. So let us look at some quantitative findings. So as you can see on the lower end, the chain and the cross model are our approaches, and we can see that we actually beat all the comparison methods. So the comparison methods here are the only ones we found in literature to be applicable on the gap filling problem without having any ancillary data or making assumptions. There are some approaches that only work if there's only 10% of the data missing, or that need a pre-trained model or ancillary information from different dates. We don't assume that, and those are our comparison methods here. And we see that we're actually a lot better. So as I said, the cross model also looks at spatial information in the neighborhood, 4-pixel neighborhood. And the chain model is a very much simpler model that is only modeling 1 pixel over time. And that makes it kind of similar to a linear or nearest neighbor interpolation, which is also listed in the table here. And what we can see is that even modeling just 1 pixel over time in a probabilistic way leads to way better results. Right. So now let us look at some qualitative results. We can compare the gap filling results, as I said earlier. So on the left-hand side, you see that cloud-covered picture, and on the right-hand side is our prediction. And what you can see is that our method and our prediction blends pretty well with the surrounding area. And we see that the gap filling obviously does have a point and works out. And that's not enough. We can also evaluate how different methods will restore clouds. So we're looking at that now. On the upper left corner, you see the ground truth data at 1 day. And on the other pictures, you see different gap filling results. Our result is on the lower right border. And what you can see is that we are actually, we think, pretty much on point. So the lin gap filling result does look a little bit more structural and a little bit, with more contrast, but the colors are kind of too bright and too crazy. It doesn't really blend well with its surroundings. While the NSPI gap filling looks kind of fitting in terms of colors, but there's a lot of structure missing. And I think our result here looks better and kind of combines both. Doesn't look that harsh and out of color, and still captures a lot of structural similarity. So let us conclude and put it all together. Probabilistic gap filling makes no assumption over data or gap nature at hand. That's, I think, one of the most important things. There are a lot of literature approaches, but they all make some kind of assumption. We also do not depend on any ancillary information or fully observed training data, which is also a very good thing and makes us very different from other approaches. We can also adapt and customize the whole probabilistic gap filling in terms of model structure or the prediction methods, and we can also come up with different priors, maybe different empirical priors, or even with expert priors and domain knowledge, and incorporate that into a probabilistic framework. And what's also important, of course, we outperform other approaches on different remote sensing datasets. So we tested 2 different datasets, both work out, captured from a different satellite, different dimensions, and it's still working out pretty well. And we implemented the whole method. It's publicly available. Just type in that URL or look in the paper. It's all in there. So really happy to see you all use that method, maybe on your own data or compare your own methods with us. Also, one important thing, this was mostly about remote sensing, but it's actually just one example application. You can use that in any kind of data domain. So thank you very much for your attention. If you have any questions, just send them now in the presentation, or send me a mail or something. And yeah, thank you very much. All the best.